All right, here's a quick, I'm going to try and be quick so it doesn't take too long. Resistor circuit analysis. This is the same circuit that we had in class the other day. So you should have already seen this. If you've already done it correctly, then this video may not be very helpful. It may be just to see the flow of things and see it quickly. So let me just analyze this. And when I say analyze a resistor circuit, what it means is I want to get all currents that are flowing everywhere in the circuit, and I want to get all voltages that are flowing, or not flowing, but are across. When I say voltages, voltage is always the idea of higher and lower, right? The laziness principle. There's got to be lower potential energy someplace. Well, that means you're comparing one area to another, one place to another. Potential energy is energy of position. So I'm comparing two positions in the circuit and looking at the difference in voltage or the difference in potential energy between those two places. And we use our voltage ladders with the colors to kind of represent the two places. And the other thing that we can do is all powers. Power is how fast we use energy. With resistors, as they use power, they get hot. So basically, it's how hot these things are getting the power, how many watts of power in each resistor. And the governing equations, Ohm's law, we have two versions of Ohm law. Resistance is voltage divided by current, and power is voltage times current. Those are the two versions of Ohm's law that we're working with. And at the outset, it's going to be using this equation over and over and over. I'll use this equation, and I'll apply it. Ultimately, I'll apply it to every resistor in the circuit. Same equation, but different resistors. All right. And when I have equivalent circuits and I combine resistors, then I can apply this equation to the equivalent resistors. And so we're just going to apply this equation over and over. So let's see what we can do. Let's first do our colors. Let's do our color map. So we'll do my hot color, and then I'll do my cold color, low voltage color. Then I go back to my hot color and I change the style. And then if I have more that needs to happen, I can go to my cold color and change the style. And so my map is going to look like this. I have my cold color, I have my dashed cold color, I have my dashed red high color, and my solid high color, and I have here to here is 36 volts, and then I have this is my battery and R1. Have those color combinations across them, so they're in parallel. And then I have this is here to here, solid red to dash red. This is R4 is across that color combination. I have here, this is R5, has the combination of dashed red, dashed blue. Then I have dash blue, solid blue. I have this here. This is R3. And I have R2, which is solid red dash blue. So let me go back here, extend this a little bit, and then I can go like this. This here, well, just do this. That there is R2. That's solid red to dash blue. Okay, those are all my color combinations and the components that are across them. I'm initially looking to see if any two components have the same colors across. And I can see that battery and resistor 1 do, so they're in parallel, but I can't make an equivalent circuit out of a battery and a resistor. Equivalent means I have to have two of the same kind of component, two resistors or two batteries. But here I have a battery and a resistor. I can't combine those into an equivalent. So there are no two resistors with the same color combination, so none of these are in parallel. And then in series, I'm looking for things that if I walk through one resistor, I must go through another, and the only one is this. If I go through R4, I must go through R5. All the rest, there are junctions. After I walk through R1, I have a junction. I have a decision to make. So there's nothing in series with R1. If I walk through R3, I have a junction, and there's a decision to make. So it's not, R3 is not in series with anything. If I walk through R2, I hit a junction. There's nothing's in series with R2. Only R4 and R5. There's no junction in this area over here. So R4 and R5 are in series. So I can draw an equivalent circuit. Here's my 36-volt battery. Here's my R1. Here's my R3. Here's my R2. So this is R1, R3, R2, and this one is going to be R45. R45. And it's an equivalent circuit of series, and in series, I just add the resistors. So I have to add 4 and 5, so I have 8 ohms. So this is going to be 8 ohms. I do my colors again. And just by way of a comment here, when I do my colors, I have to match. See, after R3 up here, coming out of R3, it was dash blue. Or after R3, it's a sloppy R3. Let me clean that up. That's a very sloppy R3. After R3, I have to have dot, dot, dash blue. Okay? Because that's what I did up here. I don't want to... I could have gone dashed red here because I may have wanted to go dashed red, but that would have been wrong because that's not what I did up here. The dashed red has disappeared because I've combined R4 and R5, so the dashed red has disappeared now in the circuit. It doesn't exist in this equivalent circuit. Okay, so now I can see that R45 has solid red dash blue across it, and R2 has solid red dash blue across it. So those two are in parallel. And so I can combine those. This is my 36 volts. This is my R1. This is my R3, right at meter this time. And this is R2, 4, 5. And this is 1 over 1 over R2 plus 1 over R4, 5. And that's going to equal R2 is 3 ohms, 1 over that. R4, 5 is 8 ohms, 1 over that. Add those together, and then take 1 over that, and I get 2.2. 2.18, but I'm rounding. You keep all the digits. And now I do my colors again on this circuit. There's my circuit now. And now we can see that R245 and R3 are in series. None of these are in parallel, but these two are in series. So I can make a new equivalent circuit. I can combine. This is 36 volts, this is R1, and this is R2, 3, 4, 5. And they're in series, and so R3 is 4 ohms. So I have to add that. Four ohms, so this is going to be 6.2 ohms. R3 is 4 ohms, right? Add that to the 2.2, I get 6.2. And now I do my colors again. And now these two are in parallel with each other. And so my final equivalent circuit. Yep. I get down to just one resistor in the whole circuit, 36 volts. This is R equivalent. And this is 1 over R1 plus 1 over R2, 3, 4, 5. All right, so this is 1 over R1 plus 1 over R2, 3, 4, 5. And R2, 3, 4, 5 is 6.2. Take 1 over that. And R1 is 2 ohms. Yes. Add those together. Take the inverse. I get 1.5. And obviously my colors are just like this. So I can see that across here I have 36 volts across here. And so I can apply my Ohm's law equation to this resistor. So I can say R equivalent equals 36 volts over I. And I is going to be the current that flows from the positive terminal of the battery to the negative terminal of the battery. Remember, the long line is the positive, the short line is the negative. Positive current flows, positive charges flow out the positive terminal, flow around to the negative terminal. We're going to call that I. That's the total amount of current flowing out of the battery. And we solve this equation. We're going to get 36 divided by R equivalent. I get 23.8 amps. Okay, that's 23.8 amps. Now, the trick is this. You then have to take this information and bring it back over to the previous diagram. Okay, this current has to come back to the previous diagram and be placed in the appropriate point, which is coming out of the battery. This is I coming out of the battery, because these are equivalent circuits. These two have to do the same thing. The battery does the same thing in both circuits. So I is flowing out of the battery. But in this diagram, we have a junction right here. And that junction is going to cause my current to split. And as my current splits, I'm going to get some of it going this way, which we're going to call I1. And we're going to call this I2. All right? So here's a principle. This is called Kirchhoff's current law. Kirchhoff's current law says that the current flowing into a junction has to equal the sum of the currents flowing out of the junction. Can't make current or lose current at a junction. It just goes in different directions. Right? So I now know, look here, I know the voltage across R1 is 36 volts, because look at the color combination, solid red, solid blue. And I know the value of R1 is 2 ohms, so I can apply my Ohm's law equation to R1, and I can say, well, R1 equals 36 volts over, and the amount of current flowing through R1 is I1. And I solve that for I1. I1 equals 18 amps, because R1 is 2 ohms. All right, so we have 18 amps flowing through there. And now Kirchhoff's voltage law says that no, don't go there. Don't go there. We'll just do this. We'll apply this now to R2, 3, 4, 5 equals 36 volts over I2. Okay? And let's just calculate this. And we're going to get 6.2. So we got 36, 6.2. 5.8. And now look. Here's I2. Don't say that. Let's do this. This equals I2. And look, Kirchhoff's current law works. If I add 5.8 amps here to 18 amps here, I'm going to get 23.8 amps, and that's what I was from back here. So Kirchhoff's current law works. The currents add up. Okay. Now we have to take this information. We have to take, in particular, we have to take this piece of information, I2, and bring it back to the previous diagram and put it in the right place. So here's what we can say. We can say that we have I coming out of the battery. We can say we have I1 flowing through resistor 1. And then we can say we have I2 flowing through the 2 resistors shown in this diagram. These resistors are in series, and we said series means if you go through one resistor, you must go through the other. Well, the current does go through the resistors. So I2 flows through resistor 245, and the same current must flow through R3 because they're in series. So now I can use my Ohm's law equation again. And I can say this. I can say R245 equals V245 divided by I2. And I2 is the 5.8 amps. So I can solve this for V245. V245 equals R245. Well, R245 is 2.2. I get 12.8. So this is the first new voltage that I've gotten. And it's the voltage, let's make sure it's clear what we've got here. V245 is the voltage across resistor 245. It's this resistance across here. I'm comparing two places. And I've color-coded the places, solid red and dash blue. So solid red and dash blue is up here. It's the voltage across this resistor. I don't see that resistor in this diagram, but it's okay. I see the color combination. I see the color combination of solid red to dash blue. And that's the same in all diagrams. And that voltage I now know is 12.8 volts. So I'm going to put that in here. This is 12.8 volts. That's solid red to dash blue. Okay. And then Kirchhoff's voltage law is going to tell me, look here. Just look at the diagram up here, the ladder diagram. 36 volts is from solid red to solid blue in one jump. It's a 36 volt jump. If I go from solid red and take a jump to dash blue and then dash blue to solid blue, I've got to get 36 volts for the total jump. I've just done it in two steps, two jumps. One jump is 12.8. That means the other jump has got to be 23. Let's see here. Let's see, 23.2. If the total jump has got to be 36, and I'm just going to take it in two steps, then this jump here of 12.8, and then another jump of 23.2 is going to give me my 36. I could calculate it with the same Ohm's law equation. I could do this calculation for resistor R3, but I'd have to come up with 23.2. Okay, so anyway, we have 23.2 now. Now we've put that information into our ladder diagram. Now we go back to the next diagram. So what we have is this. We have I coming out of the battery. We have I1 coming down through there. We have I2 going here. And then we have another junction. See, I2 is going to split now. At this junction, I2 is going to split. And so I have to define a couple new currents. So I'm going to call this let's see, 2A. I'll call that I2A. And then I'm going to call this I4. Okay. And the current law says that I2 must equal I2A plus I4. That's Kirchhoff's current law. It says that the currents coming out of a junction have to add up to the current that came into the junction. And so now I can figure out what I2A is by using Ohm's law. I can say R2 is V2. Let's see. V2, I already know. I already know this is 12.8. I don't need to put it in here. I know the number. 12.8 volts. How do I know that? I'm looking over here at my color ladder diagram. The voltage across R2 is 12.8 volts. I already know that. So I'm just going to use that information divided by I2A. And I know what R2 is. R2 is 3 ohms, so I can solve for this. So I got 12.8 divided by 3. And I get 4.3 amps. So this is going to be I2A is 4.3 amps. Okay, so and we knew that I2 was 5.8. So this was 5.8 amps. I just figured out that I2A was 4.3 amps. And so I can say that I4 is going to be 1.5 amps. Okay, that's the current flowing down through I4. All right, so I now take this information back to my original diagram. I'm going to come back through all my diagrams. So here is I. Here is I1. Here is I2. Here is I4. And here is I2A. Okay, and I4 goes through both R4 and R5 because they're in series. Okay, I have a couple of places that I don't know voltage. I don't know voltage on my ladder over here. I don't know the voltage here across R5, and I don't know the voltage here across R4. So that's my next job, is to figure those out. And I'm going to do that using Ohm's law. So I'm going to say R4 is equal to V4, which I don't know, divided by I4. And I4, we just figured out, was 1.5 amps. 1.5 amps. So V4 equals, just solve this equation for V4. And R4 is 7. And 1.5 amps. I get 10.5 volts. So I can say 10.5 volts. And now look. I know that going from solid red to dash blue is 12.8 volts. That's one jump. Here I'm making two jumps to go to the same, from the same place to the same place, from solid red to dash blue, in two jumps. I know the total jump is 12.8. I've made one jump here now of 10.5, so I should be able to figure out exactly what it is here, this one remaining jump. And that's going to be 12.8 minus 10.5, so this can be 2.3 volts. So So R5 is 2.3 volts. So now I know all the voltages and all the currents. Okay, it would probably be good for me to put this information all together in a common place. So let's see, I1, okay, is where R1 is. I1 was 18 amps. So I'm going to just put that over here, 18 amps through R1. Then we had I2, and I2 was 5.8 amps. But I2 doesn't flow through anything. Okay, so I2 doesn't flow through anything in particular. The current that flows through R2 here, the current that flows through R2, we called it I2A. And I2A was 4.3 amps. So 4.3 amps through R2. R3, the current through, oh, here, this is where, I see, okay. The current flowing through R3, right? Look here, the current flowing through R3, right here, is I2. Look, I2 splits at this junction into I4 and I2, and then those two come back together at this junction and flow through I3. Well, then it's got to be I2. So this is going to be 5.8 amps. Yes. This is 5.8 amps through R3. R4 and R5. So let's see. They have the same current through each of them. That's I4, and we said I4 was 1.5 amps. So this is 1.5 amps, and this is 1.5 amps. So I know all the voltages and all the currents. And if I wanted to, since I know all the voltages and all the currents, I could figure out all the powers as well. But I won't. We'll just end it here, okay? But this is what it means to analyze a resistor circuit. And again, I can't overemphasize the importance of these color ladders and using colors on your diagram. It just makes for, I think, a much clearer understanding of what's going on and a place to put all the numbers that shows their relationship to one another. So anyway, hope that's helpful.